Okay, so this is actually the first question that we are going to do. Okay, we want to actually talk about the strong acid, strong base situation, which is actually the simplest situation we are going to have. So in this example, you have something like this. You have 0.1 N sodium hydroxide solution, and then you have 0.1 N HCl solution with a volume of 100 ml. So step number one, okay, what we want to do is actually want to list out our titrant and analyte, right? So what is your titrant? NaOH, right? And its concentration is actually 0.1 M. Who is actually your analyte? HCl. Concentration 0.1 M. Volume 100 ml. Okay, so let's actually first step. Second step, you want to actually write out the ionic equations. So think about this. When you have a solution contains sodium hydroxide, it's strong base, right? So it dissociates 100%. Therefore, you know inside your solution, for your titrant, what's going to happen is actually you're going to have sodium plus and OH minus from your titrant. Okay, so if I make my analyte as red, okay. Then for your analyte, you have HCl, right? HCl is a strong acid, so it's going to dissociate 100%. Then you're going to have H plus and the Cl minus. They are going to interact with each other, okay? So the acid is going to interact with your base. Therefore, you know this guy, they are going to interact with each other, going to give you just H2O, and then you still have sodium plus and the Cl minus inside your solution. So the things we just finished is so-called the complete ionic equation, right? Okay. But if you look at this equation, okay, you should realize that sodium actually appear on both sides, right? So you can actually ignore it. Chloride is the same, right? So the things that actually matters and contribute your OH, it will be OH minus plus H plus. That give you H2O. That is so-called the net ionic equation. The third step is actually want to calculate the equivalence point, right? The VEP. Okay, we are going to use a concept called the number of mole of titrant is going to equal the number of mole of your analyte. Our titrant is sodium hydroxide, right? We don't know the volume, how much of sodium hydroxide I should add into my analyte so that it will reach the equivalence point. That's the things we want to solve. But for your number of mole of analyte is actually well known, right? Because you know it's 0.1 N, 100 ml. So you can actually calculate the number of mole of your analyte is just equals to the concentration of your analyte times the volume of your analyte, right? They will give you the number of mole of analyte. Number of mole titrant is actually you want to use the titrant concentration times certain volume, then to add in, right? So that the number of mole of titrant is going to equals to the number of mole of analyte. That's how we get to this part, okay? Therefore, you know your VEP is going to equals to concentration of your analyte times the volume of your analyte divided by the concentration of your titrant. Since we're in the first part, we actually know that is the concentration of your titrant. That is the concentration of your analyte, right? That is actually the volume of your analyte. Therefore, we can actually calculate the VEP very easily, right? So that's 0.1 times 100 ml over 0.1. Okay, so this will give you just 100 ml. What this means is that after you add in 100 ml of your titrant, then your system is going to reach equivalence point. So if today I say, okay, I only add in 50 ml of titrant, then you know the solution you're going to have will actually fall within zone number 2, right? Yeah. So if I say I add in 110 ml of my titrant, then you know you are actually at zone number 4. So knowing your VEP is very important because it's going to tell you which zones you are. Okay, so then we want to do step number 4, right? I want to calculate pH at different zones. Okay, calculate pH before you add in any titrant. So apparently this is actually zone number 1. Now you need to ask yourself, what solution do I have? Before you add in any titrant, that means actually the solution you have is just pure analyte, right? And then you know your analyte HCl solution, right? And the concentration is 0.1 N. So what solution do you have? Strong acid, right? So you know the proton concentration would simply equals to your acid concentration. That's going to give you 0.1, right? So pH is negative log of your proton concentration, going to equal to negative log of 0.1. That gives you a value of 1. How about the second one? Okay, if you add in 30 ml of NaOH. So the first thing is actually you want to know, if I add in 30 ml, right now I add in titrant is 30 ml. And then you know your VEP is equals to 100 ml, right? So by comparing these two, you will know you're actually in the zone 2 because the amount you add in is actually less than the amount you should have for the equivalence point. Therefore, you know you're actually at zone 2. When you are at zone 2, what do you have inside your solution? To understand this, it's better to actually write out your net ionic equation. OH minus plus H plus. That give you H2O, right? So in the beginning, you know you have 0.1 N, 100 ml of acid, right? So that's actually from your analyte. You have that many, right? And then right now you add in 30 ml of your base. Okay, concentration is also 0.1. Once you do this, you know acid bases, they are going to always interact with each other, right? So this one apparently is actually the limiting reagent. So this one will be consumed fully. Okay, so you know you're going to consume all of your base and produce that many water. And then once you reach your equilibrium, all the base are gone because they are consumed by the acid. Okay, acid is actually in excess in this case. So in the end, you have this will be 0.1 times 70, right? And then this just 30 times 0.1. So you have left many more of acid still existing inside your solution. H plus will be the one ultimately determine your pH. You want to actually know the pH, right? So you need to know the proton concentration. So right now, the things you know is actually number of mole of your OH is going to equals to 0.1 times 7, right? 70, that's equal to 7. Okay, you have 7 millimole of your OH, of your number of mole of H. Another. Okay, number of mole of your proton is that much, right? But the things that you really need is actually the concentration to calculate your pH, right? So you want to actually calculate your proton concentration. So right now you know number of mole is 7, right? What is the volume now? Originally in your analyte you have 100 ml, right? Right now you add in 30 ml of your titrant. Therefore, the total volume of your solution will be 130 ml, right? So that is actually how you calculate the concentration of your solution at zone 2. The things that is really different is that the total volume of your analyte changes, okay, when you add in different amount of titrant, okay, and that will actually affect the concentration of the proton. Okay, so this is actually the part that you want to actually recalculate the concentration. In the ice table, we always do the mole here. So we did not actually change the concentration. Okay, we actually change into the concentration later. So once you have this, then the pH will simply equal to negative log of this value. Anyone have calculators?
that a 130 down below?
Yes.
Where do we get that from?
That is actually from 100 mil of your aniline plus 30 mil of your Titration, because on the top of the question you add in 30 mil of NaOH.
Okay.
Yes. 1.27 for the pH. So you can see if you add in some of the base into that, okay, the pH go from 1 to 1.2. So here is actually relatively simple because you know you still have your aniline outweighted than your Titration. So in the strong acid-base condition, in this case, all you have is a strong acid remaining inside your container. Therefore, the solution you have is still strong acid. The only thing you need to do is actually recalculate the proton concentration due to the change of the total volume. Let's look at the part C. You add in 100 ml of sodium hydroxide. So that you know, now your V titration is 100 ml. And you also know your VEP is 100 ml, right? So you know you're actually at zone 3. Okay, at zone 3, that means actually you have the same amount of acid, the same amount of base. What do you end up with? You have the same amount of OH minus, right? The same amount of H plus. They are going to interact and consume each other because they are actually the same amount. So all of them will be consumed. All you have is what? Water. So what is the pH of water? 7, right? So the very last one is actually if today I in 100.5 ml of sodium hydroxide. Okay, so right now you know your V titration is 100.05, which is actually larger than your VEP, right? Your VEP 100. Okay, so therefore you know right now you have a solution that have already passed your equivalence point, right? So we know you are at zone 4. Okay, so in the beginning we know in our aniline we have 0.1 m HCl, right? We have 100 ml. We have that many moles of H plus. Right now you add in 105, right? Concentration of OH minus actually 0.1. You have 100.05. Okay, so that's the situation we have right now. Apparently we have more base than the acid. This becomes the limiting reagent, right? And that guy will be consumed completely. It's going to be consumed completely. That means actually into minus that much. When you reach equilibrium, okay, this will be 0 for your H plus. For your OH minus, you have 0.1 times 0.5, right? Therefore, you know the number of mole of your OH minus is simply equals to 0.1 times 0.05. But the things we care is actually the OH minus concentration, right? So you want to actually calculate your OH minus concentration, which can be obtained from the number of mole of OH minus divided by your V total. Okay, so your V total will be the volume of your aniline plus the volume of your Titration. Number of mole of your OH minus is actually 0.1 times 0.05. Volume of your aniline is 100, right? Volume of your Titration, 100.05, right? So you can actually calculate your OH concentration, okay? Then you can calculate your POH. It's going to equal to negative log of your OH minus concentration. Can you calculate that again for me? 4.6, so that's 4.6. Then what is your pH? It's going to be equal to 14 minus 4.6, right? It's 9.4. I want to actually get back to this value again, okay? So you know, before you add in any titrant, you have a pH of 1, right? And then if you add in some amount, it go to like 1.2. Okay, add in 30 mil, like go from 1 to 1.2. Okay, so you can see the increase is not a lot, right? But once you add into 100, okay, pH jump to 7, right? It actually goes up like this. It goes slowly in the beginning, but when you reach to close to your equivalence point, you're going to see a huge jump in your pH. And then after that, you just add in how much? 0.05 mil more, right? So you go from 7 to 9.4. Okay, so you can see the pH is going to change like crazy, okay, around your equivalence point. If you actually really do these experiments, which I think you are going to do this in your Jenkins experiment, right? If you plot your pH and then x-axis is the volume of your titrant, then you should expect to see something like this. Increase slowly and then shoots up quickly and then going to be like this. Okay, so once you actually map out this curve, you can actually know where is actually your VEP, right? So let's actually you have this curve, you can find out the kind of center point. That will be actually your VEP. Based on our current situations, I also want to emphasize at your zone 1, all you have is just a strong acid solution, right? How about your zone 2? You still have strong acid solution, right? Because all the base you add in was consumed. You just have less concentrated strong acid inside, but you still have zone 2 is still a strong acid solution. How about your zone 3? You have the same amount of acid base and they are going to consume with each other. Suddenly, all you have is what? Your zone 3, all you have is just water. Okay, therefore your pH is actually 7. How about zone 4? At zone 4, you have strong base goes into water, right? Then you have a diluted strong base solution. So at your zone 4, you have your strong base solution. So in this case, the calculation of your pH or pOH is very simple, right? Because all you need to do is actually calculate the amount of base divided by the final volume of your solution. Then you can get your proton concentration or base concentration. Therefore, you will know the pH of your solution. So this is actually the simplest case that you're going to have. And then here, in this case, our titrant is a strong base, right? Our analyte is a strong acid. Now I want to ask you, if I flip these things around, okay, if my analyte is a strong base, if my titrant is a strong acid, how this curve will change? In the beginning, in your zone 1, okay, all you have is actually a strong base solutions, right? Therefore, you should expect your pH is going to be larger than 7, right? Because you have strong base, so pH is actually going to be close to 14. And then when you add in acid, you can see the pH is going to decrease gradually. And again, nearby the equivalence point, you're going to see a sudden jump of your pH, right? And then after the equivalence point, you're going to have a strong acid solution. Therefore, the pH is going to keep decreasing and reach a very small value. To translate the things we just said on the plot, you should expect something like this. So this will be actually your titrant is strong acid, your analyte is strong base. So you really need to know your system, because once you know your system, you can actually predict how it should look like already. Okay, and then when you plot these things out, it's very easy for you to identify, okay, where you are. Then you know what solution you have. Therefore, you know what equation you need to use.